Hey folks, I'm Trek. Let's learn calculus. Welcome back folks, and let's just jump right into it. Today we're talking about limits, and limits are actually pretty easy at least on the surface. All they mean is that when you're talking about the limit of a function is what does this function approach, what does the value of the function approach as its input parameters approach a certain value. Let me show you exactly what that reads as. So how you'll see it going forward is it'll look like this. The limit as x approaches some value, I'm just going to write 0 here, of f of x. And you evaluate this as though it were like a function, like sine of 35. This will come out to be a value. And your first instinct should be that, how is that any different than just saying f of 0 in this case? And 9 times out of 10 you'd be right, but there's always those extra cases that make things a little bit more interesting. And let me show you what we're talking about. Alright, so the first thing I want to show you is the control case, basically. This one is just going to work exactly like you expect it to. We have our function here, which is y equals 2x plus 1. And let's say we want to know the limit as x approaches 2 of our y of x function. Well, what we do is we identify our point here, and we ask, as we get closer and closer to 2, picking values along the way, let's for example start at 1.5. Well, if we plug in 1.5, we get 4. If we plug in 1.75, we get 4.5. And as we pick values that are closer and closer and closer to 2, we get closer and closer to our value 5. On the same thing on the right side, if we start over here at 2.5, we get 6. And if we pick values that are closer and closer and closer to 2, we get closer and closer to 5. Thusly, the limit of our function as x approaches 2 is 5. So this is equal to 5. And that worked, fine. I mean, in fact, we could have just plugged in 5 into our y equals 2x function and plugged in 2 into our y equals 2x plus 1 function and gotten 5. But the problem is, the problems that arise come with basically just more complicated functions. For example, how about this one? This is the function f of x is equal to x cubed minus 1 over x minus 1. The first thing you should notice is that this has a hole at x equals 1, because at x equals 1 we get 0 over 0, which is what this hole right here is. Now if I asked you what the limit is as x approaches 1 of f of x, what would your answer be? Well, if you follow your logic from the previous example and you just plug in 1, you would get not a number. You can't evaluate that. But this function actually does have a limit, because while it has a hole here that can't be evaluated, it does approach the same value from both sides. If we pick values here, and we continue to pick values along the x-plane, each time we pick a value, we get closer and closer to the value of 3. And same thing from the other side. As we continue to pick values, we get closer and closer to the value of 3. So this actually has a limit of 3, even though f of 1 does not exist. It still has a legitimate limit. And this is why limits are useful, because they allow us to talk about holes, basically, and infinitely small numbers by addressing how things change as numbers approach other numbers. Let's move on to our next example. I'd like to show you, because I think it shows just how it shows in more detail how this can be more complicated. This right here is the ceiling function, as in the round-up function. Anything, it's f of x is equal to the ceiling of x. And that means you put in 1.5, you get 2. You put in 1.75, you get 2. You put in any fractional value, and it upgrades it to the next integer. Here's an example of us having a value at, say, let's go with f of 1. At f of 1, we have a value of 2. Or sorry, f of 1, we have a value of 1. Because 1 doesn't get rounded up. And that's right here. However, the limit, if we pick values here, if we say here, okay, we got 1, 1, 1, 1, we're still getting 1, we're getting closer and closer to 1. Oh, so it would appear our limit is in fact 1. However, if we approach 1 from the right side, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, we are consistently getting closer and closer to 2 as we approach from the right side. Our limits from the two different sides are not equal, and thus we don't have a limit. So in this case, our limit as x approaches 1 of f of x does not exist. But our function value does exist. And that leads us to our definition of the limit, and that's that a limit exists where from both sides any value you pick has another value which is closer to that. Let me just do this again. The definition of the limit is for any value x, you can pick an arbitrary value on either side, and you can pick another value closer to x which has a function value which is closer to the function value evaluated at x. Don't really like that one either. Which leads us to our definition, which reads like this. Alright, so I've obviously there you'll find it, in books and online and stuff, and much more technical jargon than this, but I felt that this was a pretty good way to phrase it if your goal is just to kind of get the basics. So we'll go through this. For any function f and x value x naught, a limit exists if you can continuously pick x values nearer and nearer to x naught, and f of x, f of the x values you're picking, is continuously approaching a particular value. And this has to be true from both sides. And then the value of that limit is y. It's the certain value that your two approaching processes are, with the value that they're approaching. Okay, so before we move on, I just want to point out that sometimes you'll run into some particular cases where we're only interested in the left or right limits, and those will look like this. And we're just going to use 0 as our example, and they'll have a plus up here. Or you'll run into limit of x approaches 0 minus. And that just means the right limit and the left limit appropriately. Those don't come up too often, but occasionally you like to talk about them, especially in talking about limits. But okay, I've got 2 more examples I'd like to show you, and then we need to move on to the squeeze theorem. So let's keep moving. Okay. So this is the function sine of 1 over x. Now this one, first off, you can't evaluate it at x equals 0. So we know that you can't plug in 0 here and get a value out. But it also does not have a limit as x approaches 0. So the limit as x approaches 0 of our f of x function here, f of x equals sine of 1 over x, does not exist. And that's because of wobbling, which is a super technical term. But all it's really talking about is the fact that as we zoom in and zoom in and zoom in, from both the left and the right, or either one, both limits from left and right both have to exist in order for the whole limit to exist. But it never approaches a particular value from either the left or the right. In fact, the further and further we get in, we can just see that it just gets more and more wobbly. It doesn't settle. So this also does not have a limit. Okay, and I have another example. Jump to. Okay, well, actually we're ready to move on to squeeze theorem. I showed you guys some examples of how limits can be the same as evaluations and how limits can be different, and hopefully from that you'll be able to sort of get an intuitive grasp of how to treat them coming in the future. They really are kind of an intuitive sort of evaluation. I mean, there's not like, you can't like do algebra on a limit really. I mean, you can still do a couple things, but they aren't super important. They will come very naturally to you. What's important is that you get sort of this sense of what to do when someone asks you what the limit is. Okay, so now we have to talk about the squeeze theorem. The squeeze theorem is the second most important thing we get from limits, I'd say, next to the derivative. But since we'll be using the squeeze theorem regularly throughout the rest of this series, it's important we talk about it. And it's really not that hard. All the squeeze theorem says is that if we have three functions, we'll call them f, g, and h, and we know the limits of f, and we know the limits of h, and we also know that f is always greater than g, and it's always greater than h, or less than or equal to, then we know that g's limit must be between f and g's limits. So let's go through this example here so I can show you what we're really talking about. Our top function here, I'm going to get rid of our text here. The red line is the function f of x is equal to the absolute value of x. So that's the red line. So I'm going to point it at it. And then we have our blue line, and this is h of x is equal to the negative absolute value of x. And then our purple line here, our purple function, is g of x is equal to x times the cosine of x. Okay, so let's first find the limits of our two upper and lower bounding functions. Our limit of absolute value of x as x approaches 0. So the limit as x approaches 0 of f of x. Well, let's take a look. As we pick values that get closer and closer to 0, we're approaching 0 from the left. And as we approach from the right, we are also approaching 0. So this has the same limit on both sides, and thus its limit exists. So this is equal to 0. And for the blue one, the limit as x approaches 0 of h of x is equal to, well, if we approach from the left, you notice we're getting closer and closer to 0, and if we approach from the right, we're getting closer and closer to 0. So that's limit is also equal to 0. So both of these functions have a limit of 0 as x approaches 0. So now we need to prove that f of x is always greater than or equal to g of x is always greater than or equal to h of x. So let's go through this. So it should be fairly clear that the red line goes from y equals negative x to 0, and then it switches to y equals x over here. So its range on the left side is from 0 to x. So x ranges, well, so we have 0 here and x up here at any given point. Same thing on this side, we have 0 here and x up here at any given point. And then the negative absolute value is the same thing. So we actually have a range in between each of these regions here of x to negative x on both sides. So we have x up here and negative x down here. Now, x cosine of x, let's just talk about this function for a moment. First off, and most importantly, let's talk about the cosine of x term. Cosine of x has a domain, or a range, sorry, it has a range of 0 to 1. It can never have a value that's greater than 0 or 1. So even if we assume that cosine of x is always at its highest value, it's not going to be any larger than x times 1, which x times 1 still falls within our range here. because this red line is x. Likewise, it can go to -1. Or sorry, its range is -1 to 1. And so our bottom possible value is negative x when it's x times -1. So at its maximum value, it has a value of x, and at its minimum value, it has a value of -x, which is between f of x and h of x. And it is between f of x and h of x throughout the entirety of its domain. You go as far off this way as you can, as far off this way as you can. It's always going to be between the two. And this is the condition we need to use the squeeze theorem. Since we know that f of x is greater than or equal to g of x across the entire domain, and you can actually use the squeeze theorem on a smaller interval if you need to, but in this case we can use the whole domain, and g of x is always greater than h of x, and we know the limits of f of x, so the limit of can't type x is equal to 0, and we know the limit of h of x as x approaches 0 is equal to 0, then we can say beyond shadow of a doubt that the limit of g of x as x approaches 0 must be between, we'll call this a, we'll call this b. So a must be greater than or equal to that, must be greater than or equal to b. It has, so in this case, it has to be between 0 and 0, which obviously there's only one value, it's 0. So the limit as x as g of x as x approaches 0 is equal to 0, because that's the only possible value. And that's kind of what we'll do with the squeeze theorem. We'll take two functions, two known functions that we can figure out the limit of, and we use them to determine the limit of a third function. And alright, now that we've covered the basics of limits and the squeeze theorem, I'm going to go through a couple of more advanced examples in sort of a bonus video, and then we're going to come back to the derivative, and we're going to finish that out and move on with that. Thank you all for watching. If you enjoyed what I do here, please like and subscribe. I don't do this for profit or anything, but it really means a lot to me if you could lend your support. Before I jump off, I do want to talk about my shout-outs to our people on the side here. First off, you got Math PFF, who I will probably be citing a lot because her videos are amazing, and is as good as I hope to be one day. I'll never be able to match up to how good she is at explaining math, so be sure to check out her videos. In addition, I've also got Carrie KH. He is one of my favorite basically visualizers. He takes all sorts of experiments and data and he puts it to visualizations that are really quite amazing, and he comes up with some great conclusions. So give him a visit as well, and besides that, I'll see you all next time.